There's more to light than just the visible part that we can see. It is characterized by energy, and depending on the energy, we give it different names. At low energies, we call it radio. A little higher, we call it infrared. And at much higher energies, we call it X-rays. We might be familiar with X-rays from X-ray machines in the doctor's office. If we were to take a picture of the sky with such an X-ray machine, we would see nothing. This is mainly because the atmosphere protects us and absorbs most of the X-rays. But what if we put the X-ray machine on a rocket and send it above the atmosphere into space? We have done this, and we have seen that there are many objects in the universe that emit X-rays. Some of these sources shine all the time, while others seem to blink. If we could zoom in on one of these blinking objects, we would actually see two stars orbiting each other. As this binary system aged, the more massive star, at least 10 times more massive than our Sun, eventually ran out of fuel and exploded in a massive supernova. After this huge explosion, all that is left is the core of the star, which we call a neutron star. Neutron stars are super dense objects, about 20 kilometers across, that rotate rapidly. Because the neutron star is so compact, it can siphon off matter from its companion. The matter is then pulled towards the neutron star. But because the neutron star is basically a giant magnet with a very strong magnetic field, the intense pressure of this magnetic field stops the matter before it can reach the surface of the neutron star. Instead of falling directly onto the surface of the star, it is diverted and follows the magnetic field like water follows pipes. This means that it reaches the surface at the two magnetic poles of the neutron star. When this matter hits the surface of the neutron star at the poles, it produces X-ray light. You can think of it like a meteor entering the atmosphere of the Earth. Its motion energy is converted into light, although the exact process is a little different. But this means that we get two bright spots on the surface of the neutron star. Because the neutron star is also spinning very fast, we can see these spots as pulses of light, like a lighthouse, coming and going. This is called an X-ray pulsar, and it is responsible for the distant blinking that we see. We can record the intensity of light over time in a light curve. And if you look at the light curve of just one rotation of the neutron star and see how the light changes during that rotation, then this is called a pulse profile. One problem we face is that we still do not know all of the details of exactly how these processes happen. Nor do we even know how much of the light we see comes from each pole. We call this the pulse profile decomposition, because we want to separate the different parts that make up the pulse profile. This is the problem I'm trying to solve using a method similar to what we do at parties. At a party, we can focus on one conversation, even if there are other conversations going on and a lot of noise around us. We can pick out the important sounds even if we don't understand how they got mixed together. This is called blind source separation. Our brains are good at this, but computers still find it hard. Still, it's not impossible for them, and there are different methods for this. Researchers are using one of these methods to listen and separate the different voices of light coming from the neutron star. But first, they had to check that some of the assumptions we talked about earlier were correct. For example, they were trying to work out whether we should actually expect to see two different sources of light from the two poles of the neutron star. What they found was that the data were consistent with expectations, which led them to believe that blind source separation technique can indeed be applied to X-ray pulsars. To see if this method really worked, the researchers did some tests. They created some simulated data, mixed it, and then used blind source separation techniques to unmix it. They tried to make their tests as close to real life as possible, and the results were great. They could actually predict how the signals were mixed. This also helped them understand the limitations of the method. They found that it works best under certain conditions. They need enough light, more than Poisson statistics, for it to work, which means they need bright sources. And they also need to observe the source for enough rotations, at least 1,000 pulses. The next step was to test the method on a real source. So the researchers studied data from an X-ray pulsar called Centaurus X3. They chose this source because it's very bright in X-rays, bright enough for our method to work. And the data they used were obtained by an X-ray instrument called RXTE, because this satellite has been observing Centaurus X3 for over 16,000 rotations of the pulsar in one observation. The new method is called phase-correlated variability analysis, or PCVA, and the researchers used it to analyze the data and review the results. The result is two contributions that look quite similar, almost mirror images of each other. However, each of these contributions is asymmetric. This is interesting because other methods looking at the same problem assume that the pulse profile contributions should be symmetrical. So there's a big discrepancy between the symmetric results and the PCVA results. How can we explain this difference? And can we trust the PCVA result? The researchers have looked at this in great detail and believe that the PCVA result is reliable. And they can also explain the asymmetric result. Essentially, the pulse profile is only expected to be symmetric if the magnetic field is perfectly perpendicular to the surface of the neutron star. If this is not exactly the case, then asymmetries can occur. And there are many reasons why there might not be a right angle. For example, because we have a dipole field and the neutron star is an extended object. Or because there could also be higher multiple components. This could cause the magnetic field to be at an angle other than 90 degrees to the surface of the neutron star, and therefore explain the asymmetric result that they get. While this research doesn't provide all the answers, it adds an important piece to the puzzle of understanding X-ray pulsars. The new method developed, called PCVA, offers a great new way to analyze these pulsars and could lead to more accurate insights into their behavior and properties. For example, PCVA helps us better interpret the pulses we observe, which could reveal new details about their magnetic fields. In addition, blind source separation, a technique that has already shown promise in areas such as signal separation in radio astronomy or analysis of cosmic microwave background data, could be incredibly useful in other fields as well. I'm eager to explore how this technique can be applied to different types of data or problems, such as the analysis of supernova remnants. That is all for today. I hope you have enjoyed this video and learned more about this research, and I hope to see you next time. Until then, goodbye.